So welcome everyone. This is our 7th talk of the webinar series on Beyond Diagonal Reconfigurable Intelligent Surfaces. The webinar series is organized by the Special Interest Group on Beyond Diagonal RIS, whose website is reported below in the slide. And today I have the great pleasure to introduce Dr. Shanpu Shen with the University of Liverpool as our distinguished speaker. So to me, this is a very special episode of the series, as Shanpu is the author of the first paper where Beyond Diagonal RIS was proposed. So I'm really looking forward to the talk. So let me get quickly started by introducing the speaker and reminding the rules of the webinar. Dr. Shanpu Shen is a senior member of the IEEE. He received a bachelor degree in communication engineering from the Nanjing University of Science and Technology in 2013, and a PhD degree in electronic and computer engineering from the Hong Kong University of Science and Technology in 2017. He was a visiting PhD student with the Microsystems Technology Laboratories at MIT in 2016. He was a postdoctoral fellow with HKUST from 2017 to 2018, and a postdoctoral research associate with the Communications and Signal Processing Group at Imperial College London from 2018 to 2020. Also, he was a research assistant professor with the Department of Electronic and Computer Engineering at HKUST from 2020 to 2023. And he is currently a lecturer with the Department of Electrical and Engineering and Electronics at the University of Liverpool. His current research interests include RF energy harvesting, wireless power transfer, reconfigurable intelligent surface, Internet of Things, MIMO systems, and antenna design and optimization. He is the 2024 IEEE Antennas and Propagation Society Young Professional Ambassador. So very briefly, let me remind you the rules of this webinar. The talk will last approximately 50 minutes, during which the audience will be muted. After the talk, there will be the Q&A session. So you can raise your hands and ask directly questions to Shanpu, or I will pick questions from the chat. And this is all. So Shanpu, the floor is yours.
Okay, let me share my screen. Yep, can you see my screen?
Yes.
Okay, thanks for Matthew's very nice introduction. And hello, everyone. Welcome to this webinar for the IEEE ComSoc Special Interest Group on Beyond Diagonal Reconfigurable Intelligent Surface. In this webinar, I will give a talk on the Beyond Diagonal Reconfigurable Intelligent Surface utilizing scattering parameter analysis. So my name is Shanpu Shen. I'm a lecturer at the University of Liverpool. In this presentation, I will firstly review the introduction and the background for reconfigurable intelligent surface. And secondly, I will introduce how to use scattering parameters to model the reconfigurable intelligent surface. Thirdly, I will present architecture design for the reconfigurable intelligent surface. Fourthly, I will present mode design for the reconfigurable intelligent surface. Last, I will conclude and discuss the future directions for Beyond Diagonal Reconfigurable Intelligent Surface. Reconfigurable Intelligent Surface, or we call it RIS, is regarded as one of the most promising and revolutionizing technologies for the next generation wireless systems. RIS can intelligently configure the wireless propagation environment by changing the surface configuration. Therefore, it can be used to enhance different communication systems like UAV communication, robotic communication, Internet of Things, or millimeter or terahertz communications. This is an example of RIS application in the 19th Asian Games. From this picture, we can see that we can use multiple RISes in the stadium to enhance the throughput of the mobile wireless network. A RIS consists of a large number of reconfigurable scattering elements. Each element can adjust the phase shift of its scattered signal. Therefore, by collaboratively adjusting the phase shift, all scattered signal can be added constructively or deconstructively at the receiver. Therefore, we can use this to improve the channel gain or suppress the interference or increase the energy or spectrum efficiency. Currently, most work of RIS focus on the system optimization, but ignore the physical and electromagnetic fundamentals. Therefore, in this presentation, I will show how to use scattering parameter network analysis for modeling, and architecture design and mode design. So in the next part, I will focus on the modeling of reconfigurable intelligent surface utilizing scattering parameter analysis. As a starting point, let's see a toy example for network analysis. Consider a transmit antenna here and a receive antenna. These two antennas are separated and embedded in a wireless propagation environment. Therefore, these two antennas can be viewed as a two-port circuit network. We can denote the voltage and current at the transmitter antenna, that is port 1, as VT and IT. Also, VR and IR are voltage and current at the receive antenna, that is port 2. From the traditional circuit theory, it is well known that the voltage and current at the two ports can be related by the impedance matrix Z of the two-port network. And with such Z matrix, we can analyze the relationship between the transmit voltage and current voltage. And also we can find the channel expression. So this is a typical example for Z parameter analysis. However, in this presentation, I will focus on another equivalent parameters to analyze the network, that is scattering parameter or S parameters, which is very popular actually in microwave engineering and antenna engineering. So let's first briefly review some preliminaries for scattering parameter network analysis. For a transmission line terminated by a node ZL, there exists an incident voltage wave and reflected voltage wave. The superposition of the incident and reflected voltage wave is actually the total voltage across the transmission line. And the ratio of the reflected and incident voltage wave is defined as reflection coefficient, gamma L, which has a 1-to-1 mapping to the node ZL. And here, Z0 is the reference impedance for calculating scattering parameters. Typically, it is set 15 ohm. The terminated transmission line is essentially an one-port network. Therefore, we can further generalize this idea to n-port network, and we can denote the incident voltage wave and the reflected voltage wave at the nth port as AN and BN. And further, we can use a scattering matrix X to relate the reflected and incident wave at all the ports. Therefore, we can find that actually reflection coefficient is essentially the scattering matrix for one-port network, written in the scalar form. Okay, with these preliminaries, let's try to analyze the example of the two antennas in the scattering using the scattering parameters. Now we have the AT and the BT. So this means the incident and the reflected waves at the transmit antenna. And we also have AR and BR. That is the incident and reflected wave at the receive antenna. The incident and reflected wave also can be related to the voltage and the current. For example, if we add the incident and reflected wave, we will get the transmit voltage. And if we subtract the reflected wave from the incident wave and over the reference impedance, we can get the current. So this is the relationship between the incident and reflected wave between the with the current and the voltage. Okay, we can use a 2x2 matrix S matrix to relate the incident wave and receive a reflected wave. And also the S matrix has a 1-to-1 mapping to the Z matrix. Using the two antennas, we can build a simple single input and single output communication system. At the transmitter, the antenna is connected to an RF source that consists of a voltage source and a source impedance. Therefore, we can relate the incident and the reflected wave at the transmitter by this equation. So here, BST refers to the source wave generated by the voltage source, and gamma T is the reflection coefficient of the source impedance. On the other side, at the receiver, the antenna is connected to a node impedance ZR. Therefore, the incident and reflected wave at the receive antenna are related by this equation, and gamma R is the reflection coefficient for the node impedance. So this is like we have an incident wave BR impinging to the ZR, and then reflected by ZR. So now we have four linear equations characterized by scattering parameters. Therefore, it allows us to solve the four unknowns, AR, BR, AT, and BT. Therefore, we can solve these linear equations to find the incident and reflected waves at both antennas. To further simplify solving the linear equations, we can make some practical assumptions. First, we can assume that the transmitter antenna and the receiver antenna are both perfectly matched. Therefore, the STT and the SRR, these two parameters are zero. This assumption is practical because generally for antenna design, the aim is to have a reflection coefficient as small as possible. We can also assume perfect impedance matching, which means that the source impedance and the node impedance are both 15 ohm, the reference impedance, so that gamma T and gamma R are zero. This is also practical because standard RF source and node generally are selected as reference impedance 15 ohm. So with these two assumptions, we can greatly simplify the linear equations. And then we can find the reflected and incident wave as this. So this is very, very easy to solve. So this allows us to find the voltage at the transmit and receive antenna VT and VR. Therefore, if we define VT as the transmit signal X and VR as the receive signal Y, we can relate X and Y by this equation. So this one implies that the S parameter SRT is essentially the channel gain for the SIG communication system. Therefore, we use the auxiliary variable HRT to represent the channel gain. It's essentially the SRT. Well, in practice, the S matrix of the two-port network can be measured by an instrument called the Vector Network Analyzer, VNA. The measured SRT is essentially the channel gain between the transmit and the receive antenna HRT. Therefore, the channel model utilizing S parameter is measurable and can be verified experimentally. So far, we have seen that scattering parameter is very useful and straightforward to characterize the channel model for the SIG communication system. Next, we consider a slightly complicated example as shown in this picture. So on top of the SIG system, we consider that in the propagation environment, there is an extra antenna connected to the node ZI. That is this. So this can be actually viewed as a single element arrays. Well, although this is very simple, but we use this to demonstrate this channel model. Similarly, these three antennas can be modeled as a three-port network, which is characterized by a 3x3 S matrix. And also, at the transmitter and the receiver, the incident and reflected waves are regulated by the same relationship as the previous example of SIG. Particularly at the race, AI and BI refers to the incident and reflected waves at the antenna at the race. And AI equals to theta multiplies BI. And theta is actually the refraction coefficient for the node Zi. Particularly if the race is lossless, we have the Zi is a pure reactive, that it can be a capacitor or inductor. Correspondingly, we have the theta has a unit constant, which can be represented as the phase shift. Similar to the two-port case, now we have 6 unknowns and 6 linear equations characterized by scattering parameters. So we can solve these linear equations to find the incident and reflected waves at all 3 antennas. Again, we can assume that all 3 antennas are matched so that these S parameters are 0. And also we can assume perfect impedance matching for the transmitter and receiver so that gamma T and gamma R are 0. And this allows us to greatly simplify these linear equations. And we can therefore find the reflected wave and incident wave at the transmitter antenna and receiver antenna. Similarly, we can link the transmitter signal X and the receive signal by using the scattering parameters. Well, it should be noted that here we have a term STI theta SIT. This term actually represents the double reflection from transmitter to race and back to transmitter. This term is actually very small, therefore we can ignore it, and therefore we can further express the channel by this equation. Recall from the two-port example, we know that actually SRT, SRI, and SIT are the channel gain between the transmit, receive, and the race antenna. Therefore, we introduce auxiliary variables HRT, HRI, and HIT to represent these equivalent S parameter and write the overall channel as this way. So now you can see this is consistent with the widely utilized race channel model. The two toy examples have demonstrated that it is very useful to use scattering parameters to model the race channel. For a general modeling for race, we can consider the multiple antennas at the both transmitter, receiver, and race, especially race, because generally this is an array of antennas. Therefore, we can use similar scattering parameter analysis for this race-aided wireless system, like this. And actually, you can see that these equations, they are exactly the same as the previous example, but with an increased dimension. Previous is scalar, but now is vector. For example, here theta is a diagonal matrix, and each diagonal entry is the phase shift. Similarly, we can solve these linear equations to find the channel matrix. Again, to simplify solving the linear equations, we need some assumptions. Particularly for the multiple antenna case, we need an extra assumption that there is no mutual coupling among the multiple antennas at transmitter, race, and receiver, so that the sub-block matrix STT, SII, and SRR are 0 matrix. And with these two assumptions, we can simplify the linear equations and finally find the channel expression. So you can see now this channel expression is exactly the same as the widely used race channel model, showing that the scattering parameter is very useful. However, at the same time, we should understand this channel expression is implicitly based on some assumption, for example, no mutual coupling. Scattering parameter analysis is also powerful to characterize the impact of hardware imperfection on the race channel modeling. If we don't make any assumptions, actually we can still solve these equations, although it's very complicated. And we can find the corresponding channel expression for the race channel. So this is comprehensive to incorporate many factors like mutual coupling at the transmitter race and receiver, and the imperfect impedance matching at all the sites. In addition, if we want to investigate the mutual coupling issue at the race, we can assume that only mutual coupling has existed in race, and the other part are perfect. Therefore, SII is not 0, and then we can find the channel expression like this. Now you see the channel expression is a nonlinear function of the theta. It's no more linear relationship like the conventional race. So this tells us that actually scattering parameter network analysis is very powerful to characterize and model race, even including the hardware imperfection. In the third part, I will introduce the race architecture design using scattering parameters. From the race modeling, we know that an inanimate race can be modeled as n antennas connected to an input reconfigurable impedance network with its Z matrix denoted as Zi. And for the conventional race, each antenna is connected to a codable impedance component like this. And we can see antennas, they are not connected to each other. So there is no signal flow between the two pairs of antennas. Therefore, for this kind of architecture, the corresponding Z matrix and S matrix are both diagonal matrix. And if we assume lossless race, so Zi is purely reactive and theta is a diagonal phase shift matrix. So this is actually the widely utilized constraint we use for conventional race optimization. However, we want to ask a question. Is this architecture the most general? What if we connect each pair of antennas with a tunable impedance component like this figure, right? We connect each pair of antennas with an extra component. We refer to this architecture as fully connected race, while the conventional architecture as single connected race. For fully connected race, now the Z matrix of the reconfigurable impedance network is no more restricted to be diagonal. It can be full matrix. And the corresponding S matrix theta satisfies these equations. This means that this is passive device. There is no power amplification. And this tells you the relationship between the S matrix and the Z matrix. Particularly if we assume lossless race, so that Zi is pure reactive, is imaginary matrix. Therefore, we can represent our theta as a complex symmetric and unitary matrix. So this is more general and provide more degrees of freedom than the conventional diagonal matrix. And that's why we refer to it as beyond diagonal race. In addition, if we use non-reciprocal material like ferrite for circulator, so Zi and theta can be further relaxed to be asymmetric. But of course, it will increase some circuit complexity. So for fully connected race, it becomes complicated when the number of elements is large, because we see each pair of the antennas, they are connected together. So it needs much more tunable impedance component, which increases the circuit complexity. Therefore, we proposed a group connected race architecture as a trade-off between the single connect and the fully connect case. Specifically, as shown in this figure, we can divide the race element into G groups, and each group has NG element and use fully connected architecture. For example, here we have 8 antennas together. We divide it into 2 groups. So each group has 4 antennas and they are connected. They are fully connected. Or we can divide the 8 antennas into 4 groups, and each group has 2 antennas and use fully connected. Therefore, the corresponding S matrix for the group connected architecture is a block diagonal matrix, and each block is complex symmetric and unitary. Again, it is beyond diagonal. This is a special case for beyond diagonal race. We consider an race-aided decisive system to demonstrate the race optimization with different architecture design. For simplicity, we just ignore the direct link and we try to maximize the received signal power, subject 3 different constraints for the S matrix of race. For single connect architecture, theta is diagonal phase shift matrix. For fully and group connected case, the theta is unitary or block diagonal unitary matrix. For the single connected architecture, we can find the maximum received power as this equation. So in this equation, we first multiply 2 channel vectors element-wisely and sum the absolute value and square it. The optimal theta to maximize the received signal power is given by this. Each phase shift is seen as the negative phase of the channel gains product. On the other hand, for the fully connected reconfigurable impedance network, we can use the Cauchy-Schwarz equality and leverage the property that theta is a unitary matrix. Therefore, we can find an upper bound for the maximum received signal power. So the upper bound is the square of the 2 channel vector norms product. So we take the norm first and we multiply them together. Therefore, the optimal theta to achieve the upper bound should satisfy this equation. See, this means that if we want to achieve the upper bound, we need to find a unitary matrix theta so that it can rotate the direction of the vector HIT to the direction of the vector HRI Hermitian. So this is showing that it is shown that the theta there is a closed form solution for this equation, and also numerical simulation results show that this upper bound is tight. Further, using Cauchy-Schwarz equality, we can find the fully connected case achieves a higher or equal power than the single connect case. Particularly, the condition to achieve the equality is that the magnitude of the 2 channel vectors are linearly dependent. However, such condition is hard to satisfy for multipath propagation channel. Therefore, this means that generally fully connected architecture is better than the single connected one. What's more, for group connected architecture, because it is a trade-off, therefore it is easy to show that the performance of the group connected architecture is in the middle. So let's consider a specific scenario for the race-aided decisive system. So we assume the transmitter-receiver receiver channels are really fading, and the transmitter-race channel is rise and fading, and we assume the distance-dependent path loss model and set different path loss exponent for the 3 channels. Therefore, we can find using the Monte Carlo method, we can find the average received signal power versus the number of race element using 3 different architectures: single connected, group connected, and fully connected. So from the simulation results, we can find that first, the average received signal power increases with the number of race element. So this shows that race is very useful to manipulate the environment to enhance the wider system. Second, we can see that the fully connected race achieves the highest power. This is because the corresponding constraint is most general. It has the most general architecture. Third, we can find that the group connected architecture is in the middle. This is because it's a trade-off between fully connected and group connected. Besides, if we increase the group size, we can achieve a higher received power, but it is achieved at the expense of more complicated topology. We also show the power gain of the fully and group connect case over the single connect case. So we can see that the fully and group connect architecture can increase the power by up to 50%. In addition, the power gain is decreased with the rising factor. So this is because when the rising factor is large, the 2 channel vectors are more likely to be linear dependent. We summarize the performance of the 3 race architectures in this table. We compute the power gain of the fully connection and the group connection over the single connection. We can find that the group-connected architecture achieves a good trade-off between the complexity and power enhancement. So it can increase the power by up to 22% with only requiring half more components. So in the fourth part, I will introduce the mode design. So far, we have shown the advantages of group and fully connected architectures. Then we wonder how to further leverage the advantages of group and fully connected architecture. For the conventional race, when a transmitter sends a wave to the race, the race will reflect the wave to the same side of the transmitter. That is here. So we refer to this mode as reflecting mode. However, this limits the performance of the race since only half space is covered. That is, only this space is covered. The other space is not covered. Therefore, to broaden the coverage, we keep the circuit, but change the antenna orientation. For example, previously we have 4 antennas towards the left side, but now each side we have antenna. And because group and fully connected architecture connect antennas, this allows the signal flow between the 2 antennas. Therefore, when we have a wave impinging to the race, it can not only reflect the wave to the same side, but also go through the circuit and then transmit the signal to the other side. So this enables a full space coverage. And therefore, we refer this model as hybrid transmitting and reflecting mode. Again, we can use scattering parameters to characterize the hybrid transmitting and reflecting mode. We consider a transmitter here and K users. Some users are at the one side of the race and the other users at the other side of the race. And for the race, we assume it has M cell, and each cell contains 2 antennas. Therefore, the M cell race is modeled as a 2M antennas connected to a 2M port reconfigurable impedance network. Accordingly, we can write the overall channel matrix between a transmitter and all users as this equation. Be careful, now the dimension for the S matrix of the race, phi, is 2M by 2M. And if it is lossless, the matrix is unitary. To derive the channel model for the hybrid mode, we can make 2 assumptions. First, each antenna has the unidirectional radiation pattern. So this assumption can be achieved by using, for example, microstrip patch antenna or some conventional antenna with quarter wavelength reflector. So these can achieve a unidirectional radiation pattern. Second, we assume that each antenna in the cell are back-to-back placed. This can be easily achieved just that you oriented the antenna and you can achieve this back-to-back configuration. Therefore, we can divide the race into 2 sections. Each section cover a half space. And also we can partition the overall channel matrix as this. So this is the equivalent expression, but just written in a block matrix form. From the 2 assumptions, we know that users in one side are not covered by the antennas at the opposite side. Therefore, this means that some matrix, some sub-block matrix are 0. For example, this one are 0. Leveraging this 0 matrix, we can simplify the channel expression as this. Further, we can define user 1 to K1 as reflective users who are on the same side of the transmitter, while we can define the other users on the opposite side as the transmissive users. Therefore, we can rewrite the simplified channel as these equations. Here, we rewrite the submatrix phi 1, 1 as phi r, which means the scattering matrix for the reflecting mode. And also we can rewrite the matrix phi 21 as phi t, which represents the scattering matrix for the transmitting mode. Therefore, originally we have this constraint for the whole scattering matrix. This is a unitary matrix. So this is equivalent to say the summation of the power for the reflecting mode scattering matrix and transmitting scattering matrix is a unit constant. We just decided the power allocation for reflection and transmission. Depending on the architecture of the reconfigurable impedance network, the scattering matrix for the two modes, phi r and phi t, they could have different constraints. For fully connected architecture, we assume each race cells, they are not connected to each other. So this means that the two scattering matrix, phi r and phi t, are both diagonal. And the summation of the diagonal entry power is unit constant. But on the other hand, we can also assume a fully connected architecture so that all cells are connected to each other, and the corresponding constraint is the most general, like this. Well, to achieve a trade-off between the complexity and the performance enhancement, we can consider a group-connected architecture. So we have M cells divided into G groups, and each group utilizes a fully connected architecture. So that phi r and phi t, they are block diagonal matrix. And each block diagonal matrix satisfies these conditions. So we also provide some numerical results to compare the three modes, reflecting mode and transmitting mode and hybrid mode. And for each mode, we consider three different architectures, including fully connected, group connected, and single connected. We consider a race-aided MISO systems and compare the sum rate. So from these two figures, we can find that hybrid mode is better than reflecting mode or transmitting mode. And also fully connected architecture is better than group connected architecture, which is better than single connected architecture. In addition, we can find that for the same architecture, the performance enhancement for the hybrid arrays is prominent in Ricean fading environment. So this is because hybrid arrays can fully utilize multi-user diversity, while other parts of the users are blocked under other modes. So now we have seen the advantages of hybrid transmitting and reflecting mode. We wonder how to further utilize this to enhance the hybrid mode. Is there any more general mode design for race? To answer this question, we observe that for hybrid mode, it has two sectors to divide the whole space into two parts, the one for reflection and the other for transmission. Therefore, we consider further increasing the number of sectors so that each sector covers a portion of the space. It's just like the sectors utilized in the cellular network base station, and we call this mode as multi-sector mode. For example, if we have 6 sectors and each sectors cover 60 degrees. Therefore, this multi-sector race can cover 330 degrees, cover the whole space. To model the multi-sector BD-RIS, we consider a transmitter, multiple K users, and M cell race with L sectors. We also make the following 3 assumptions. First, in each cell, there are L antennas, which are placed as a polygon, such that each antennas cover 1/L space, a small portion of the space. Second, each antennas of the race has a unidirectional radiation patterns with beamwidth 2π/L. So this assumption can be implemented by using some high-gain directional antennas with a narrow beamwidth. For the third assumption, we assume that transmitter and user K1 users are located within the coverage of the section 1, and generally there are KL users located within the coverage of section L. So actually you can find these 3 assumptions a generalization to the hybrid mode with 2 sectors. So with this assumption, we can see that a multi-sector BD-RIS has LM unidirectional antennas, and it is modeled as an L-sector polygon prism like this. So now for multi-sector mode, the beam width for each antenna in each sector is narrowed, right? We assume the beam width is 2 pi over L. So this means that it has a pattern covering this area. So the pattern means for antenna means the spatial distribution of radiated power of the antennas as a function of the angular space. And from the pattern, we can define the beam width. For example, half power beam width, which means the angular separation where the power is equal to half. So the pattern and the beam width actually are related to the antenna gains by these equations. This equation tells us that the beam width is inversely proportional to the antenna gain. Therefore, if we use a narrow beam width for the multi-sector BD-RIS, we can increase the antenna gain. And from theory's transmission equation, we know that increase the antenna gain can increase the channel gain. Therefore, this demonstrated the benefit of multi-sector BD-RIS that using direction antenna can help to increase the channel gain and therefore enhance the wireless system. Here is an example demonstrating the difference between the reflective mode and multi-sector mode. So we see both modes utilizing the group-connected architecture. Right here, all of them are connected. But for reflective mode, all the antennas are arranged toward the same side. For this case, they only cover the half space. However, for multi-sector mode, now we have 4 antennas. Each antenna covers a quarter space. So in total, this one covers the whole space. At the same time, because the beam width is now quarter space, so it can increase the antenna directivity and therefore increase the channel gain. To derive the channel model for the multi-sector mode, again, we can partition the channel matrix, just like the hybrid mode. Since each sector covers a portion of the space, users in one sector will not be covered by the other sectors. Therefore, some submatrix are zero matrix, and we can leverage this to simplify the channel expression like this. So you can see this is a generalization to a hybrid mode. Furthermore, for the scattering matrix, we rename phi L as phi L1. That is the scattering matrix for each mode, for the sector L. Therefore, the original constraint will become this. So this means that the power for each sector is constant unit. Similarly, depending on the architecture of the reconfigurable impedance network, the scattering matrix for each sector, phi L, have different constraints. For single connect architecture, again, we assume the RIS cells are not connected to each other. Therefore, phi L is diagonal matrix. For fully connected architecture, we assume all cells are connected to each other, so it has the most general expression. And for group connected architecture, again, we divide the cells into G groups, and each group utilizes fully connected architecture, so that phi L is block diagonal matrix. We provide the numerical results demonstrate the performance of the multi-sector BD-RIS. So we consider a multi-sector BD-RIS aided the multi-user MISO system, and we maximize the sum rate. So these two figures shows the sum rate versus the number of antennas in the BD-RIS at different number of sectors, like 2, 3, and 6. From these two figures, we can find that first, the sum rate of multi-sector BD-RIS enhances with the growth of number of sector L. So this demonstrates the benefit of using multiple sectors in BD-RIS. Second, given the same fitting condition, multi-sector BD-RIS with a smaller number of antennas but larger L, that is here, achieves the similar performance with large number of antennas, but with smaller area here. Again, this demonstrates the benefit of using multi-sectors in BD-RIS. Third, we can find that the performance gap between multi-sector arrays with different Ls increases with the rising factor. So this demonstrates in rising feeding, it is more beneficial to utilizing multi-sector BD-RIS. Overall, this numerical result demonstrates the advantages of multi-sector BD-RIS. To summarize, in this presentation, we have introduced 12 cases for beyond diagonal arrays with different architectures and different modes. For each case, we have a constraint for the scattering matrix, either be a diagonal, block diagonal, or a full unitary matrix. So this actually provides a very flexible methodology for the BD-RIS design and optimization. You can choose the corresponding constraint for your particular optimization problem, and there are also many algorithms to solve with these different constraints. Actually, we also have some other architecture design for BD-RIS. For example, tree-connected arrays. So this means the BD-RIS has a graph, which is a tree. So for tree-connected arrays, it has the least complexity, but it can always ensure to achieve the upper bound on the received signal power. And here are two examples for the tree-connected arrays. We can either connect this or connect by this. Due to the limited time for this presentation, I just briefly introduced the concept of tree connection, and more details can be found in this reference. So in the end of this presentation, I would like to briefly conclude this presentation. We first show that scattering parameter network analysis is very useful to model arrays. And the widely utilized arrays model is implicitly based on certain conditions. And based on the scattering parameter analysis, we introduced two architectures designed for BD-RIS, including fully connected arrays and group connected arrays. Fully connected arrays can achieve the optimal arrays performance, but with highest complexity. For group connected arrays, it can achieve a good trade-off between performance and circuit complexity. Therefore, it is a very feasible solution in practice. In addition, we have demonstrated two modes design, including hybrid transmitting and reflecting mode, which achieve the full space coverage. And based on this, we have proposed the multi-sector mode, which not only achieves the full space coverage, but can further improve the channel gain by utilizing highly directional antenna. For the future research directions, BD-RIS is an emerging and promising technology, and there are many interesting problems to be explored. These could include three aspects. First, it can be a BD-RIS design, optimization, and signal processing. We can focus on, for example, learning optimal RIS architecture, or explore the fundamental trade-off between performance enhancement and circuit complexity. And also we can focus on the channel estimation and the BD-RIS optimization. The second aspect is about the wireless use case. For example, we can utilize the BD-RIS wave manipulation flexibility for different functions of wireless, like communication, sensing, localization, power transfer, security, and channel text, or a combination of these multi-functions. We can also try to find the best use case and the deployment for BD-RIS. The third aspect for future research is about the prototyping and experimentation. For example, we can focus on designing efficient reconfigurable impedance network to enable a flexible BD-RIS. And also we can focus on reducing the circuit complexity and cost to enable the widely application of BD-RIS. So that's all for my presentation, and thank you for your listening. So any question and are welcome. Thank you.
Thank you so much, Shanpu, for the very clear and interesting talk. And yeah, if there are any questions, please feel free to unmute yourself and directly ask the question or type the question in the chat. Okay, I have a first question I will read it from the chat. For this various BD-RIS architecture, which methods would you suggest for optimal channel estimation in the BD-RIS aided systems?
Well, for each architecture, it's very good questions. So for channel estimation, actually each architecture, they can do channel estimation. So, but I think my suggestion is using the group connected, because here. Yeah, use this architecture, because this one can be further combined with some strategy, also called grouping in the channel estimation, by leveraging the correlation between each element. So using this group connection can further decrease the complexity for channel estimation. For example, we can decrease the dimension for the pilot signal by leveraging the correlation. And then we can use some compressed sensing method to do the channel estimation.
Yeah, thank you, Shanpu.
Yeah.
Please, Professor Nosek, I see you are raising the hand.
Yeah.
Please.
Well, Shanpu, thank you for an interesting talk with many interesting ideas. I have a rather basic question. Could you show us, please, your slide 17?
Okay. Yes.
Yeah. If I look at the basic equations at the bottom of that slide, the question is SRT or HRT, which should be the same, is that actually the pure direct channel which remains if I take away the RIS?
That's a really good question. That's a really good question. So for this kind of question, we always, actually in previous literatures, they just assume that we ignore the indirect term and assume that HRT is the case that we remove RIS. But this is not entirely true.
Okay.
If we consider an ideal case, for example, we consider minimal scattering antennas like dipole. For these antennas, if we make this antenna open circuit, so it is equivalent that they disappear. It is like we remove them. Therefore, in this case, if we want to find the channel without RIS, we just need to make this theta as a diagonal matrix with all entry being 1. That is, means the open circuit connected. But we should understand that this is only true for minimal scattering antenna. So minimal scattering antenna is ideal antenna. For general antenna, at least they will have some scattering. Therefore, theoretically, it's very difficult to use this, for example, HRT or SRT to represent the channel removing RS. Actually, it's very hard to find. The trade-off, the compromise is that we consider minimal scattering antenna and make theta as open circuit connected.
Yeah, I see this argument, and I see the limitation to minimum scattering antennas, but the whole multi-port approach where we control everything from the variables at the ports, may it be incident and reflected waves, or may it be voltage and current. This is in general restricted to this type of antenna. The whole model world wouldn't be true if we don't assume these minimum scattering antennas.
Yes, you can use, if you just want to have a theoretical analysis, you can use Z parameters. This can help you to investigate the case without RIS. But in practice, for communication, you need to do the channel estimation. You need to, when you do the channel estimation, actually your antenna is connected to 15 ohm. You can never, it's very hard and impractical to say I measure the channel between the antennas with open state, right? It's very hard. Actually, we measure the channel when the antenna are connected to an RF source and node with 15 ohm. So that's practical. Therefore, from this point of view, using S parameter to characterize RIS is more practical and useful. And also, this is consistent with the widely utilized channel model. Actually, this problem appears before this analog analysis. Actually, people from communication society, they directly use this channel model for race optimization, but without further exploring the fundamentals, the physical and electromagnetic fundamentals. And this is widely utilized. Therefore, I try to make it consistent with the antenna theory or the microwave theory. That's why you see use S parameters is very helpful to bridge the two areas together. And now everything is consistent.
Look, I would say no matter whether you use scattering parameters or impedance parameters, that doesn't make any difference. They are equivalent to each other. One could be converted to the other one. And it's a matter of taste, but if you like more the scattering approach or more the impedance or any other multiport matrix approach.
Yeah, they are equivalent.
Of course, for measurements, of course, scattering is the way to go because there is the equipment to measure. But for theoretical derivations, all of them are equivalent. And my experience definitely is that the impedance matrix approach is more appropriate because, for instance, that fact that these HRT is not only the direct channel has not been unveiled with the scattering parameter approach, but it comes via the impedance parameter approach. So this is a matter of taste, which one you would prefer. Anyway, the whole thing here, the whole theoretical derivation is not investigating the properties of non-minimum scattering antennas. They don't show up in that multiport approach, at least up to now. I think it would be worthwhile to think about making models for non-minimum scattering antennas and look how that could be accommodated in the multiport theory approach. This is a question where I think this is one of the open questions which we have to approach. And by the way, in your following slides, when you have looked at the SISO system, you have again used that approach that if the direct channel is blocked completely, then all what the RIS is doing is adjusting phases. It is also adjusting amplitudes. That is an important difference which should be taken into account. Anyway, but I thank you for a nice tutorial presentation.
I agree with you. It's exploring the long minimum scattering antennas for RIS or even for just a conventional MIMO is a very interesting and open problem and need more effort.
For RIS, even more. For the MIMO, if it's simply a MIMO link, then whatever happens at the receiver, I'm only interested on what the receive power is, which I can get out compared to the noise and optimize signal to noise ratio. But the RIS, there's a very specific situation that the RIS antennas are used for transmitting and receiving simultaneously. And that gives the whole thing a different twist, which makes really a difference for the actual analysis. The important thing is in non-minimum scattering antennas, there will be current on the antenna, although the port current is zero.
Yes.
And that is up to now in these multiport network analysis approach not taken into account. This is an effect which is not captured here. And I would repeat that it's a worthwhile goal to look into that and to find a way to capture that effect such that we have with the multiport analysis also catered for non-minimum scattering antennas, which is not the case up to now.
Yes, I agree. So yes, maybe using Z parameters, we also have one work that unify all the different parameter network analysis. And we would like to say that each parameter, they have their own strengths to analyze a particular problem. Especially, for example, like as you say, for using Z parameters, it may be very helpful to investigate the case that it's directly blocked or we remove the rays by considering the minimal scattering antenna. And thanks for your very nice suggestions. Okay. And yeah, I agree. There are a lot of fundamental and physics problems to be explored. We just try to make the theory consistent and harmonic with the communication. Yeah, thank you.
Okay, thank you very much.
Mathieu, I think you are on mute.
Yes, yes. Thank you. Thank you, Professor Nosek, for the question and the insight. Thank you, Shanpu, for the clarifications. Any other questions from the audience? Otherwise, this will conclude our talk. Let us thank again our speaker, Dr. Shanpu Shen, for the very interesting talk and very clear talk about modeling of RIS and architectures, mode of beyond diagonal RIS. And in 2 weeks from now, we will have our last talk of this webinar series. And see you there. Looking forward to see you there. Thank you again, Shanpu.